Hello, good morning, everybody. Sorry about that. Hopefully you can hear me now. So hello and welcome, and thank you for joining us today for the Embodied Carbon Network's 2018 webinar series. This is the fourth session of an 8-part education program, and it will focus on carbon emissions from building materials. We have several exciting speakers joining us today who will highlight guidance, initiatives, and case studies focused on better materials decision-making throughout project phases. My name is Tina DeLeggi, and I'm a program manager at the Carbon Leadership Forum. I'll moderate today's session. Please note that this webinar is being recorded and will be made publicly available later on. So many of you joining us today are already in the Embodied Carbon Network, but we do have some guests in the audiences who we invite to learn more and think about joining. The Embodied Carbon Network is a communications and knowledge sharing platform that was launched by the Carbon Leadership Forum about a year and a half ago. The network brings together individuals working in or with the building sector together to share resources, engage in discussion, and organize to take action. The network has evolved into a vibrant, engaged global community. To date, we are over 290 professionals from across the building sector, academia, nonprofit, and government groups, representing 90 cities across the world. While on the ground, our work to reduce carbon emissions may manifest in different types of research and development, technical work, tool building, education and outreach, and so forth. We connect under a shared mission to eliminate emissions from the built environment in order to meet carbon neutrality targets by 2050. So again, the network was convened by and is largely supported and managed by the Carbon Leadership Forum, or the CLF. The CLF is an industry academic collaborative based out of the University of Washington, led by Kate Simonin, that carries out research, education, and outreach initiatives focused on embodied carbon tracking and reduction. So thank you to the CLF and its sponsors for supporting the network and this webinar series. So again, today's webinar is the fourth session of an 8-part series. Each topic is based off network task force topics, and task forces are developing the curriculum and selecting speakers for each webinar. This is part of our goal to increase knowledge and provide educational resources around embodied carbon in the building sector. We have a depth of knowledge and expertise from our network members, and this is one of hopefully many initiatives we will lead to help harness and translate the knowledge more broadly. So we hope that these webinars will not only be useful to live participants, but serve as free resources in the long term to anyone interested in learning more. So please feel free to share webinar recordings with your colleagues, networks, and students. And if you are an AIA member and you need educational credits, this course is eligible for live attendees to receive credit. So today's materials webinar will include 5 presentations and a 15-minute Q&A session at the end. So please submit your questions through GoToWebinar, and I will track them and direct them to the appropriate speakers at the end of the session. So we have with us today Erin McDade from Architecture 2030, David Diaz from EcoTrust, Brad Benke from Element Architects, Leif Johnson from MKA, and Dave Walsh from Selling Construction. So Erin's going to kick us off today with an overview of material selection in the larger carbon story. David's going to share information on the carbon benefit embedded in FSC certified wood. Brad is going to talk to us about studying and comparing the embodied energy of materials in common wall assemblies. Leif's going to talk to us about LCA specifications to request quantities and supplier-specific EPDs that have been developed to help improve the accuracy of LCAs. And finally, Dave will present on the Helen Sommers building case study, which will highlight working with suppliers to produce optimized concrete mix designs and new EPDs. All right, so Erin, I'm going to hand over to you now. All right, so Erin McDade is a program manager for Architecture 2030, where she brings a background in architecture with a focus on sustainable building research and analysis. Erin holds a Master of Architecture degree from the University of Washington, and she worked at the Integrated Design Lab in Seattle before joining Architecture 2030. At the IDL, she helped to develop Targeting 100, a tool for deep energy retrofits and aggressively sustainable new construction in the healthcare sector. During that time, she also completed lighting and thermal analysis on the Revolutionary Bullet Center. She currently leads Architecture 2030's Products Challenge and is one of the founding members and current chairs of the Embodied Carbon Network. And she sits on the advisory board of the Carbon Leadership Forum. So thank you, Erin, and take it away.
Thanks for the introduction, Tina, and good morning, everyone. Thank you so much for joining this webinar. I'm really excited to get started, and as Tina mentioned, I'm going to kick this conversation off with really kind of setting the stage and the big picture for why we're here and why we're looking at embodied carbon and looking at material selection specifically. So, excuse me. Okay, there we go. So just to start off quickly, I know we are all aware of this, but in Paris in 2015, globally, we decided to some pretty aggressive climate targets at the least to keep our global temperature increase to well below 2 degrees Celsius and to try to limit that increase to 1.5 degrees Celsius. And quickly what this means in terms of looking at the data and what our global targets are. So the Intergovernmental Panel on Climate Change releases emissions projection scenarios every few years. And prior to Paris in 2015, they released a series of 4 projection scenarios for our global emissions. So you can see, you know, a business as usual scenario, pretty bad, going all the way down to this emissions peak in 2020 scenario, which gave us a 66% chance of meeting that 2 degrees Celsius goal, which was not fantastic. So in response to Paris and to the 1.5 degree Celsius goal that was a little more aggressive, the IPCC released a 5th emission scenario that gave us an 85% chance of meeting that 2 degrees Celsius goal, so much better. But what this shows us is that we really have to peak global emissions from the building and power sectors around the year 2020. So we're really getting up on that right now. And then we have to be phasing out all of those emissions by the year 2050. And just quickly what this looks like in terms of our 1.5 and 2 degrees Celsius goals, the 4 original emission scenarios, including business as usual, have us popping well above that 2 degrees Celsius line. And once we're above that line, the temperature increase just spins out of control and there's no way to pull it back down. But this most aggressive scenario shows us quickly popping over the 1.5 degrees Celsius line, but never reaching to 2 degrees Celsius, and then slowly but surely pulling back down and indicating that we would be able to actually stabilize and normalize our temperature. So this is a pretty crucial goal for the globe. Luckily, in the building sector, we have this tremendous opportunity. So as most of you are probably aware, the building sector is the single largest contributor of GHGs globally, and urban environments alone represent 75% of all GHG emissions. And we are expecting tremendous global floor area growth to accommodate a population that will essentially double in size by the year 2060. So over the next 3 decades and really ongoing beyond that, but between now and 2050, we expect 2 trillion square feet of new buildings to be constructed worldwide. And just to give you an idea of the scale of that, that's essentially in New York City once a month, an entire New York City, all 5 boroughs once a month, for 32 years. And really this is, again, this is only to 2050. This is expected for the ongoing future in New York City once a month. And so here today, of course, we're talking about embodied carbon. So it's important to look at, you know, given those goals and given that new construction growth, what does this look like for our embodied carbon emissions? On an annual scale, or on a global scale, sorry, on an annual basis, building materials and construction and building operations represent the biggest piece of the global emissions pie, with building materials and construction being responsible for about 11% of total annual global emissions. And this, you know, this pie chart is one that we've been looking at in the building sector for a while, and it shows building operations being a bigger chunk of the pie. So a lot of our efforts to date on reducing the impact of the built environment have been on building operations, and that makes sense. But our efforts to reduce building operation emissions are succeeding, not as quickly as they need to, but they are succeeding, whereas we have made almost no impact on our efforts to reduce embodied emissions. So not on, a 1 year at a time basis, but for the whole life of a building, we'll zoom down to just look at one building right now. What do the impacts of embodied versus operational emissions really look like? So again, this is one building. It's a typical high performance commercial building, an office, you could say, roughly meeting today's operational 2030 challenge target, which is a 70% reduction from baseline. So it's pretty high performance, and that comes with some associated embodied carbon penalties, primarily for a higher performance envelope. So on day one of this building's life, which was constructed in 2015, all of the emissions that have been emitted so far are embodied carbon. And none of the emissions so far, obviously, it's day one of the building's life, are operational carbon. And of course, the thing about embodied carbon is that once we put it into the atmosphere at all, it's there. So the embodied carbon stays through the life of the building. And despite a 100-year lifespan for this high performance building, you can see that after 100 years, the operational emissions are still lower than the materials and construction emissions of this high performance building. But we don't even care so much about a 100-year lifespan of a building, because remember, we have that really crucial 2050 deadline. So what if we look at this building profile, but instead of going out 100 years, we draw the line in the sand at 2050, when we need our embodied and operational emissions globally to be zero. So for this building, built in 2015, obviously the breakdown becomes much different, and that materials and construction piece is significantly impactful. And then of course, the closer to 2050 we construct a building, the bigger the chunk of the emissions will be associated with embodied as opposed to operations. So what if we zoom out for a minute from that single building scale and think back to that 2 trillion square feet of new construction that we're expected to build between 2015 and 2050? And again, assuming we draw the line in the sand at 2050, so a building built in 2049 only has 1 year's worth of building operations to show in this pie, what does that 2 trillion square feet of buildings look like in terms of emissions? So building operations alone are 10% of the pie, which means materials and construction represent 90% of the building sector emissions of this new construction for this time period. Now, it's important to note that this chart is, in some senses, our worst case scenario chart, but really what the chart is right now is our business as usual chart. This chart is showing that we are making progress on operational emissions reductions, which we are, but as indicative of our trend so far, we have not made a ton of progress on building material emissions. And so the piece of the pie by the time we get to 2050 that's associated with embodied carbon is pretty significant. So I have some key takeaways from this information that are important for us to think about as we're moving forward and looking at design. The first, just to reiterate, because this is really crucial, we have 32 years to get to zero carbon. So that means that we can't measure impacts based solely on a building's fuel lifespan. When we're doing life cycle analyses, we really need to look both maybe at the building's whole lifespan, but what do those numbers look like when we draw the line in the sand at 2050? And then second, relatedly, when setting performance targets, it's really crucial to balance the operational savings, both goals and reality, with associated embodied carbon penalties. So of course, in an ideal world, we are trying to design for both zero operational emissions and zero embodied carbon emissions. But the way it typically works right now, when we're trying to eke out those last few drops of operational savings, those often come with some pretty high associated embodied carbon penalties. And it's been our mentality so far to, save as much as we can with operations and just keep driving that number down, down, down. But when drawing that line in the sand at 2050, it becomes more important to think, okay, is the embodied carbon, the extra embodied carbon that I'm going to emit to eke out that last, 1 EUI reduction in operational savings, and that embodied carbon is going up today and it's going to be in the atmosphere, is that really worth it? And so to that end, and I'll just do a quick introduction to this new initiative that Architecture 2030 is working on right now. It's kind of coming, and some folks on this call, in fact, are even probably helping support us on this. So this is something you guys should keep your eyes out for. We are working with the Carbon Leadership Forum on an initiative called the Carbon Smart Materials Palette. And so we're trying to address a couple of problems with this. As we know, this just pulls out the building sector pieces of that larger pie. And so when you look at just the building sector, operations right now are about 72% of annual global emissions, whereas embodied carbon is about 28%. But we have made really insufficient progress in achieving our embodied carbon emissions reductions. And of course, that's resulted in a substantial gap in our progress towards meeting that 0 by 2050 goal. And so the Carbon Smart Materials Palette is intended to support immediate action for making impactful embodied carbon reductions. And we do this by providing a set of attributes and design guidelines. And this is opposed to data-based information that you might find on an EPD, for example. And the palette will have swatches for each of the highest impact products and systems, so concrete, steel, aluminum, finishes, etc., as well as complementary swatches for naturally low and no carbon alternatives that can either be used in general or used in lieu of some of these high impact products and systems. So this is coming, and the Carbon Smart Materials Palette will really be a whole toolkit set targeting all audiences that are really going to be crucial in driving our embodied carbon emissions down to 0. So the Carbon Smart Materials Palette itself will be an free online platform, and primarily for designers within the design community. Then the attributes within the Carbon Smart Materials Palette will be developed into model specifications. So again, for designers, but also then, for contractors and suppliers, etc. And then finally, the attributes in the specification language will be developed into a low embodied carbon policy toolkit to support us in our activism, but to also support legislators in successfully implementing legislation such as Buy Clean Washington, Buy Clean California, and these other embodied carbon bills that we're seeing coming down the line. So that's my quick update on what Architecture 2030 is doing. If anyone has any questions about the palette or any interest in participating in helping us develop those attributes and answering other questions about these materials, feel free to reach out to me. Thank you.
Great, thank you so much, Erin. Thanks for setting the stage and describing the challenge at hand. Our next presenter is David Diaz. So David is from Seattle, Washington, and works as the Director of Forestry, Technology, and Analytics for the nonprofit EcoTrust. He holds a BA in Environmental History from Harvard University, an MS in Soil Science from Oregon State University, and is 2 years into a forestry PhD at the University of Washington. David has spent the last 10 years working professionally at the intersection of forest ecology and management with conservation financing, markets, and policy. He has worked as a reporter covering domestic and international carbon policy and markets based in Washington, D.C., and has contributed to several carbon offset accounting protocols for forestry and agriculture projects, now in use by all 3 of the major carbon offset certification standards in the USA, including the first protocol for improved forest management adopted by the Verified Carbon Standard. So thanks for joining us today, David, and take it away.
Great, let me unmute myself first. Well, thank you for having me here. I'm really excited to share some of the work that we've been doing at EcoTrust with you. And kind of building on some of the topics that Erin teed up for us, I really want to highlight that, there's a very clear importance that the choices that we make in the materials that go into buildings have in terms of the embedded carbon footprint there, and that there's a real time sensitivity for moving in a direction where we're drawing down carbon. And so what I want to focus on in this presentation here is kind of what that opportunity is to green the supply chain further upstream for one of these building materials, and that's going to be focused on wood. And so kind of why do we care about this? From a global perspective, forests are very important to the global climate system. Apart from having, local impacts in terms of where our clean drinking water comes from, where a variety of different species are able to thrive, we can also significantly influence the global carbon balance by how we choose to manage our forests. And here in the Northwest, we kind of are blessed with one of the most productive ecosystems on the planet. Our coastal forests, particularly in Western Oregon or Washington, rival every other ecosystem on the planet in terms of how much biomass they can store, how much carbon they can suck out of the atmosphere. And obviously that's attracted a lot of investment, primarily in terms of timberland management and things like that. And so this kind of brings up this question that a lot of people are wrangling with right now as Oregon and Washington start looking at climate policy, is what can we do to manage our forests to store more carbon? And so the way that we originally got pulled into this was several years ago, we contributed to this study of the Bullitt Center. It sounds like some of you may be familiar with the Bullitt Center already, so there's a little bit of a blurb right there if you want more background information. But we were asked to do this kind of ecosystem service assessment of what's the kind of footprint beyond carbon that went into the construction and operations of that building. And one of the areas that I really focused on in that was the Bullitt Center sourced its wood from FSC certified forests. And so we were asked to quantify what kind of difference did that make in terms of the carbon benefit that the building would be providing. And so this is separate from something like wood product substitution for non-wood products and things like that. And this is just about how does the fact that the forest was managed to FSC specs change the embedded carbon benefit that's associated with that wood relative to buying uncertified wood. And so the basic idea here is that FSC represents something of a middle path between managing for timber extraction and recognizing that there are conservation values that we as a society want to have reflected in the way that our forests are managed. And so FSC certification is one of the certification options that are available. It's the only one that actually requires you to go above and beyond state regulations in terms of adopting particular types of management systems or conserving additional forest attributes. And so we developed a study that focused on two of the key requirements for FSC certification, one of which is green tree retention. And what that refers to is how many trees you leave whenever you do a harvest. And the other is riparian management zones. So how intense you can manage next to streams. And usually those practices are restricted by states that have Forest Practice Act regulations to prevent sediment from getting into streams, to protect fish habitat, and then also to protect drinking water supplies. And so FSC requires management to go above and beyond state regulations in both of these categories. And so I'll give you a sense of what some of those look like on the ground. So this is an overhead view of a coastal Oregon watershed that's been pretty intensively managed. And so just for scale here, you've got this 120-acre clear cut that's been implemented over the past several years. And you can see some of these streams across the landscape. So this is the regulatory stream buffers that would be implemented under Oregon state law, okay? So you can see that it changes depending on what type of stream it is. On the main stem here, we have some wider stream buffers than we do elsewhere. But this is what those buffers would look like under FSC practices. And so these are all areas that are being managed less intensively if you were to follow FSC rules. And as you could imagine, there's a big trade-off that happens there, both in terms of the timber output that you would get, but also the amount of carbon that you're now going to be storing by leaving trees standing in these riparian corridors. So the other aspect that we're looking at is green tree retention. So if we start with a forest that looks like this, there's a few different ways that you could implement a harvest. And so on the left here, this is showing a 10-acre area and what it would look like if you were harvesting it under forest practice rules. So this requires you to retain 4 trees per acre. It's actually 2 standing trees and 2 downed trees. So we're trying to be a little bit more conservative here of actually assuming there's more conservation than is likely to actually be happening under state forest practices. But under FSC, the most intense harvest that you can get is this 10%. You have to leave at least 10% of the basal area, which is the cross section of the trees across the landscape. You have to retain 10% of that in a harvest. So in general, within FSC, we would expect landowners, if they are implementing harvest, to range between this 10% and 30%. And as you can see, it's a lot more trees that you're leaving behind. And so we wanted to evaluate what that might look like, what the impact would look like over time. And so we selected a bunch of different properties all across Western Oregon and Washington. And we selected them intentionally to try to cover large properties and small properties, properties with lots of stream cover and no stream cover. And then we simulate 100 years of management. And we do 3 different scenarios here. So there's one that's business as usual, which is a short rotation of about 40 years with minimum retention requirements and minimum riparian buffers under state law. And then we simulate 2 FSC type scenarios where we're going to be following the green tree retention and riparian protections that FSC requires. And so this is a glimpse. This is a paper that we're preparing to submit for peer review at the end of this month. So some of these numbers are still in flux, but some of the key takeaways that we had was that when we look at tree carbon, what we see is that leaving more trees on the landscape kind of gives you this step function over time, where under business as usual, the amount of carbon stays flat, but under FSC, you start stepping up over time. Carbon storage and products decays after it's harvested. So that's a really important aspect of when you're doing the carbon accounting of forest management, that you recognize that wood products carbon is not a permanent sink. We generally found that FSC always stored more carbon than business as usual did. And there's a trade-off with how much timber you're pulling off the landscape as well. And so when we try to boil that down into what's the embedded carbon number, so if you were to buy 1,000 board feet of logs from an FSC certified forest, what's the difference that makes in terms of how much carbon is stored there? And for what it's worth, the way that we're approaching this is that we were trying to make very conservative assumptions that err on the side of assuming there's more conservation that happens under business as usual than is likely to be the case. So these numbers here are intended to be kind of the minimum estimate of what the FSC carbon benefit would look like. And what we found was that per 1,000 board feet of logs, the numbers were different in Oregon versus Washington. Washington has a variety of stricter forest conservation practices that it requires than Oregon does. So adopting FSC in Oregon would correspond to about a 1.9 ton of CO2 difference per 1,000 board feet of logs that you bought from an FSC forest versus business as usual. In Washington, it's a little bit lower, but it's still, both of these are substantial improvements over business as usual in terms of how much carbon is embedded in the wood that you're buying. And we've done a little bit more here that kind of tries to daylight what the trade-offs are as well. I'm not going to dive too much into any of these numbers, but you can get a sense of what the balance of carbon is stored under different management scenarios across the landscape. And I'll leave it at that.
Great, thank you so much, David. Thanks for sharing your work with us. We are going to go over to Brad right now. Brad, I'll make you presenter. So Brad Banke joins us from Element Architects in Seattle, Washington. As part of the firm's green team, Brad leads office-wide life cycle assessment research and project-based studies to reduce the embodied energy of Element projects and to develop LCA standards for the firm. Brad is also a LEED accredited professional, the co-chair of AIA Seattle's Committee on the Environment, and a contributor to the University of Washington's Carbon Leadership Forum. So thanks for joining us, Brad, today. Take it away.
Can you hear me?
Yes, we can hear you, Brad.
Sorry about that. Okay. Yeah. So this was just I wanted to, and thanks again for having me on the panel here. This was a study that we did at Element Architects when we were first kind of starting to get our feet wet into the LCA world, and I thought it was a good opportunity here just to note that this is kind of on the architect side where a lot of the building decisions are getting made. Just one thing that we can do, and one way to get sort of dive into doing LCA at your own firm. So I'll share how we kind of approach that at LMN. So we, one second here. So we design a lot of large urban projects, and we're a pretty big firm, so we are definitely contributing to the New York City every 35 years or 35 days. So we focused on operational energy for quite a while, and more recently have started to focus on embodied energy as well. And the way that, and one way to break that down would be to look at the structure, the enclosure, and the finishes. And one way to focus your efforts would say, we're going to ignore the site work and systems that go into it just because there's not really a lot of good data available for it, and it's sort of out of the control of a design team. So typically, what you'll find for embodied carbon is that the structure is almost always the biggest impact. Enclosure usually follows behind that, and then typically finishes behind enclosure. So there's sort of this downward trend. So certainly the most important thing that architects, engineers, designers could focus on would be the structure. However, there's a really unique opportunity for architects in particular to focus on the enclosure because it's just really easy for us to do, and we do it we design, enclosures and facades all the time, and it oftentimes does not have a lot of, cross-discipline coordination, or it's something that's mostly in the architect's hands to do. So it's a huge opportunity to take that, relatively high impact of the full building and try to make some reductions on it. So again, it's something that architects do every day. It's this versus that. What are we going to clad this with? How are we going to insulate it? What's going to be the framing? And each of these different materials, trying to develop an LCA sort of intuition as you're designing and making decisions like this as an architect, so that you can make less impactful buildings in the future. So what we did, again, this was one of the first sort of studies we did a while back, just to kind of get a sampling of some of the stuff that we've already done. So we took 10 of our projects. Some of them were built or under construction or under design. Took a single wall type from each of those, an opaque wall, and just said, let's compare those and just see where they stand. Let's just do a benchmark and see how those different walls compare against each other. And like I said, there was a lot of different types, different geographic regions, different functions. But the important thing was that we were doing our own buildings and making it relevant to our own firm. This information that we were looking at was going to be able to kind of bring it back to those teams to show and try to make a sort of an office-wide understanding of embodied carbon. One thing we had to look at was, well, what are we going to measure? Typically, the Tracy impacts, and specifically the ones used for LEED V4 were what we chose to record for this study. And then, but how are we actually going to compare these? So there's a lot of different ways we could do that. And I guess I won't get into all of them, but the point here is that we chose to just eliminate the scoring, or sort of the ranking or the comparison of these, just to look at the embodied carbon. And we're still going to measure everything else, but just for this one study, let's at least just compare them in one consistent way and eliminate the variables to just make it as straightforward as possible. So again, the goal, we'll get that information, we'll give it back to our like 150, 160 employees, and hopefully that can kind of create a culture of bringing that sort of design intuition back into the projects or back into the wall assemblies that you're designing next time. I would like to call it sort of like a playfully competitive approach, so that when people saw their own projects, they were like, oh, well, why is our project so much worse than somebody else's? So it wasn't meant to shame anybody for having a high embodied carbon wall. There's a lot of reasons that go into making the choices for a wall type or an assembly. And like I said, typically embodied carbon isn't very high on that list. There's structural concerns, there's thermal concerns, there's all sorts of things that would dictate what type of assembly you create. But adding this as one of those layers for a designer to start thinking about was the goal here. And this is what we ended up with, sort of scorecards for each individual project. A typical one looks like this. This is one of the highest ones. So the important things here are providing the wall detail, just saying what's in it, what they use, giving it the overall rank for embodied carbon, the impacts by material in the top right. So we could say, this particular wall had a lot of cast in place concrete. That was the yellow in that diagram. So from there, we could make some very easy key takeaways in the bottom right, so that if somebody gets confused by the data or the wall detail or any of the acronyms for all the different things, they could at least just take some rules of thumb to say, like, if this stuff is way over their head, they could still at least make these sort of rules of thumb decisions on the next time around. So I'll skip through most of them. I'm not going to show you all these, but this was one that landed somewhere in the middle, was a typical brick facade that we usually do. And the least embodied carbon was actually some upgrades that we were making to an existing stone wall. And there was lessons learned in all of them, but when you compare all of these as a whole, it was obviously clear, like, these are not apples to apples. These walls are doing different things in different parts of the country. So what we did find interesting was, let's at least look at some that are similar. We do a lot of university projects, so we end up doing a lot of masonry walls. And 4 different ways that could have been done were sprinkled in throughout this sort of evaluation of 10 walls. And what that ended up looking like is, the precast with thin brick was what we used for this smaller portion of the study to say that's the baseline. And then let's look at these other ones compared, since that was the highest, and what are they doing right, or what are they doing different? That gives us the same sort of architectural aesthetic, but might have different sort of embedded embodied carbon impacts. So again, the precast concrete made up a huge chunk of the first one on the left. Brick over metal panel is definitely not a typical assembly. There was some other reasons that project chose to go that way, but you can see that the spray foam and the metals, although giving you kind of the same look as brick over metal stud, is going to have a pretty huge impact. And then pretty typical for an architectural detail of a metal wall would just be a brick over metal stud. But even within those assemblies, we found some sort of opportunities to make reductions. So the one on the right, the lowest one, actually used a slightly smaller or slightly different brick module, which gave the brick a tiny bit less impact, and then also having mineral wool completely outboard of the studs, rather than also a smaller layer of mineral wool and bat insulation, also gave us a pretty good reduction as well. But at the end of the day, we're looking at this and, well, what could we actually do to go further? The brick is kind of the constant that you just can't really get rid of. So we kind of took a step back and said the thin brick, but what if we use that on a different type of assembly? And there's a lot of them out there that you could use, but let's just evaluate one of those to see what it looks like, because it's not a typical assembly that we would spec, but we had the assumption that it would probably be a pretty big reduction from the business as usual. And we were right, it was quite a significant reduction. So this is just sort of meant to be a lesson learned in, architects have the ability to do most of this stuff and just do it. You don't need to, a lot of it doesn't cost more money, a lot of it doesn't cost more time. It's just an opportunity to really drill down at the material level and start making more informed decisions. So a couple takeaways again, this was quite a while ago now that we did this study, but a couple takeaways, because I know that it's really confusing to start getting into doing LCA. But my advice would be to, start small and set some rules. I would highly recommend not trying to just say, we're going to do a whole building LCA and try to get, lead credits for it or whatever it is you're trying to do, because I think you'll get lost in the details and probably make a lot of mistakes. So I'd say start small, pick 2 curtain walls or 3 different concrete mixes, but just set some rules and eliminate variables to make it easy on yourself. Number 2 would be to forget perfection. When I shared this study with our firm, it was a lot of people were saying, oh, we didn't actually use that water-air barrier. And it's like, okay, but that's going to be a very, very small amount. You got to focus on the big picture here. And that's true for data as well. You might be uncertain about the data that you're using, whether whatever software you're using or database. But there's still a lot of progress that can be made with what's available, and I would highly advocate for going down that route. Number 3 is make it relevant to your firm, and just evaluate stuff that you use. Pick things that you're doing all the time, so that everyone in your firm will invest in it and relate to it if it's something that they've used or worked on. When I brought that study back to the team, it was way more impactful for people to see theirs compared to somebody else's, and know exactly what they did on that project and see how a different project might have done it differently to have less embodied carbon. Number 4 would be to reach out. If you're on this call, it's already a great way. The Embodied Carbon Network is a tremendous resource for all things life cycle assessment related and embodied carbon. But also look into your own firm. There's people that are going to be really interested in this kind of stuff, and try to find those champions in your own firm to sort of lead the way and start changing firm standards and things like that. Number 5 is you really just have to get your hands dirty and learn by doing. You just have to do it. And that is probably the biggest takeaway is you don't start to really understand this stuff or develop that intuition like I was talking about without kind of going through the ringer a few times and seeing where all these different impacts are coming. With that, thank you very much. Please let me know if you have any questions.
Great, thank you so much, Brad. And there are some questions coming through, and I'll make sure that they get to Brad at the end. And just a reminder, if you have questions as our speakers are presenting, just use the question function and I'll make sure that they get to them. All right, so we are gonna hand over to Leif now. So Leif is a principal and key member of MKA's Cultural Specialist Group. His design experience includes performing art venues up to 12 stories, 2,000 seats, and 80,000 square feet, a 10-story expansion to a world-renowned museum, renovation in addition to a historic 500,000 square foot landmark museum, and 2 geometrically unique science centers anchoring a new cultural district in Saudi Arabia. Leif leads MKA's Wood Techno Specialist team and has applied his expertise to the designs of the Lincoln Park Zoo South Pond Edition in Chicago, Illinois, and LeMay America's Car Museum in Tacoma, Washington, both winners of National Wood Design Awards. So thank you for joining us today, Leif, and over to you now.
Great, thank you. Yeah, and as I think Tina mentioned, I'm a structural engineer, but I believe I speak for our whole AEC industry in that we need to find efficient ways to update our specifications to request LCA information from the contractor. So the LCA specs are really a necessary tool in our mind to achieve the goals that we just discussed. And we had mentioned this before, but structural engineers, we have an obligation to do this. Almost a third of the embodied carbon of a building is due to us, right? So we have to do our part in this process. And I think that these LCA specs are important, whether you're pursuing LEED version 4 credits or whether or not your project just has sustainable goals. And we have tools that we use in design, right? Tally, I'm sure some of you are familiar with these, Athena. A lot of times Tally is nice because it plugs right into Revit, but obviously there's multiple tools, but that's only part of the story. To truly get an accurate LCA at the end of a job, we need to tap into the knowledge of the contractor. We need to know where the materials were produced, how far they came from, how are they constructed, how much waste was involved. Obviously in our structural drawings we show sticks of rebar, but there could be, of course, some waste that we don't understand, and even potentially end of life results. What happens to those materials after the life of the building? So we need to tap, like I said, into the contractor's knowledge, because the contractors know the actual material quantities, where they're procured, and how they're constructed. But what's really key in this is we need to create a standard request, right? We want to eliminate the variations between structural engineers to standardize that request. So the specs should look the same, whether they're from MKA or Thornton Tomasetti, Walter B. Moore, et cetera, so that we create a level of comfort of what's being asked. And that's how we feel like we can change the industry, that if contractors are used to seeing the same thing being requested project to projects, as opposed to different ways, depending on the structural engineer or the different project. So obviously, I'm not going to walk through our specs because that'd be extremely boring. I'm going to highlight what we've been doing past year or so. We've produced a Division 1 section to provide background of LCA. So it's titled Sustainable Design and Life Cycle Analysis Product Requirements. And we've actually had some people use these, and they've taken snippets from that and put them in other portions of their specs. But the idea is we want to at least have a section that could be standalone that would give the background for LEED version 4 or these other sustainable goals and LCA in general, so that it's more of the foundation for also the material specific sections we created. So you have your cast in place concrete, your timber, steel, masonry, etc. We've added language that you can insert into those sections. So for example, this section, cast in place concrete, there's a whole portion on environmental product declarations. And what we've also done is tried to move away from industry standard EPDs. We want to create a change in the industry where it's supplier specific EPDs are the norm. And so, it's written to try to incentivize that during the bid process. And also what's very important in these material specific sections is quantity reporting. We want to ask for all the quantities and also where each material was obtained. And so, for example, this is from the reinforcing section of the total mild reinforcing weight, and it could even get broken down into the different parts of the building. We've had some feedback where obviously some of this stuff could generate a cost uptick, but we don't know for sure until we start getting them out there. And of course, there's a learning curve, right? As this becomes more normal in the industry, maybe then the cost impact is less. But that's the key, is that we need actually these specs to be used, and then we want feedback so that we can continually improve them. So what's actually great about the timing of this webinar is that today we just finished version 2 of the specs. So we've had a bunch of really intelligent feedback from some folks around the industry, some that have used it and some that have not, but just are very knowledgeable. We've tried to scrub the originals, and those will be up on the Carbon Leadership website soon. So if you actually go to the University of Washington Carbon Leadership Forum, and under the initiatives, you can download these specs and then provide feedback. And so that's the idea, is we want these to actually be used, and that's the way we're actually going to generate change. And then of course it's a continued process, right? We look for feedback, and then we'll continue to evolve and improve them. So thank you.
Great, thank you so much, Leif. And lastly, we have Dave Walsh, and Dave is actually the task force chair of the materials group, and took the lead in putting together today's session. So thank you, Dave. I'm going to go ahead and hand over control to you. All right, so Dave is a registered architect and a director of sustainability and design integration at Selling Construction, where he leads sustainability efforts on deep green projects, including the new State of Washington, Helen Summers office building, Federal Center South, and a new corporate headquarters for a Seattle technology company. Informed by his dual experience in architecture and construction, Dave collaborates with architects, engineers, manufacturers, and owners to find materials that move projects beyond business as usual. Specifically, he has worked to reduce the embodied energy and greenhouse gas emissions in new concrete mixes. He has chaired the AIA Seattle Public Policy Board and was a board member of both AIA Seattle and the Seattle 2030 District. So thank you, Dave, and go ahead and take it away. And Dave, we can't hear you right now, and GoToWebinar is showing me that you need to enter the audio pin #70#. So if you can, give that a try. All right, you should be able to talk now.
Okay, are we good now?
Yeah, great, thank you.
Okay, great. Well, I'm happy to join this, and Leif had talked about the need to work together with the contractor and to get supplier-specific EPDs. So this case study did that. It's a new office building for the state of Washington. It's in Olympia, Washington, on the Capitol campus. And I just want to talk a little bit about our journey of wanting to optimize concrete mixes and then to generate mix-specific EPDs for this project. So just a little bit about the project. It's a design build project, and I think that actually the way that this was delivered enabled us to be a little bit more nimble and to make these kinds of asks of the concrete supplier. It was started back in 2014 and then just completed last fall. And the structural system on this, it's concrete. It's primarily post-tension concrete slabs. And you might ask, so why did you go with concrete in Washington State, a timber-producing state? And there's a couple reasons for that. So one reason was that it's across from the Capitol Dome, and so no building can be higher than the Capitol Dome itself. So that necessitated a very thin structural system, thin floor plates, and just to get the program in, concrete seemed like a good choice. Another reason for that is that there were 2 batch plants and a quarry actually within 15 miles of the site. So it seemed to be a good match structurally and to meet our program. The team on this, the architect was ZGF out of Seattle. The structural engineer was KPFF. The concrete was supplied by Cal Portland, and Sellen was the design builder. So as I mentioned, this was a competition, and we were looking to differentiate ourselves by providing optimized concrete mixes and to provide EPDs. So there wasn't an outright requirement for lower carbon intensity materials, but the state of Washington is very focused on carbon in general. In fact, this project has a performance guarantee to, reach an EUI target. So definitely a focus on the operational side. We wanted to bring that to the embodied side. The other thing is we saw that this project could be pivotal in changing the market here in Washington State. There were just 5 EPDs for mixes produced in Washington State prior to this project, and so we thought this would be a great opportunity to change that. And we also had a willing and ready supplier of Cal Portland to partner with us. So this slide is a little bit probably review, but I just wanted to recap the connection between cement and embodied GHG. Obviously it starts as limestone, goes into the kiln, and then you have the process of calcination. So that's what's happening in this red box. That's kind of where all the action is happening in terms of the major impacts of cement. And so the solution to that, that's what's happening in the green box. I know it's probably kind of small, but that's where we can replace some of the cement that we would have in the mixes with supplementary cementitious materials, be it slag or fly ash or something like that. So I know that, when people start to talk about greener concrete, sometimes the discussion goes to the percent of the SCM, but really it's more about removing the amount of cement per cubic yard of concrete place that will lead to the greatest GHG reductions. So this is an overview of the process. There's a lot of information here, so I'm going to highlight some on the next slide. But what I wanted to show with this is how you need to bring several different parties into this process, from creating new mixes to actually getting to new EPDs. Personally, I think it all starts with the owner and the owner's mandate to do something, and that empowers the team to actually, do something other than business as usual. The green bars are the structural engineer's input. What's really key is getting the performance criteria. The orange bars are the general contractor's input. That starts with estimating the volumes of different types of concrete, understanding the magnitude of the opportunity, and then at the back end, doing the final calculations of what was placed and what's the amount of GHG reduction. The purple bars are the concrete supplier, and you can see that their involvement, at least in this project, started back in DD, which is great. Earlier the better, because they need all the time they can get to do their R&D, their cylinder testing, things like that. And then lastly, the blue bars at the bottom, that was the EPD development and the work of the LCA practitioner. So just to highlight a few key moments in all of this, as with everything, start early, but to start early because there's going to be likely a schedule and a budget implication. So that needs to be accommodated while the schedule and the budget are still in formation. Talking to your structural engineer early on, as early as possible, and seeing if, at least for some of the mixes, could there be a change in the maturity dates from maybe a more traditional 28 days to 58 days. The selection of a concrete supplier early on, again, allows them to have that time to do their R&D. The bubble number 4 is sort of at the bottom of the screen. It says mock-up. And if you look carefully, it's kind of shaded, which means that we actually didn't do it. We ran out of time. You can see how that would have overlapped with our actual placement of the concrete. That was a big lessons learned because, you know, what happens in a cylinder test and a cylinder break is very different than things perform when you're, you know, placing it in massive quantities. And then finally, you can see that we were going through this process for the first time. So there were no previous EPDs with this manufacturer, at least at these plants. And so by the time we actually published, that was well into construction. So obviously not too late to inform the design decisions of this project, but that gives us the information to be smarter with the next projects now that we have the data. So with those project-specific EPDs and the you know, national baseline and our poor logs, we could basically do the math. And so this is how it came out for a specific mix. The maximum reduction, you know, per the baseline was 58%. For all of the concrete used on the job, there was a 31% reduction based on national baseline. And then if you were comparing it among similar mixes in the Pacific Northwest, it was a 27% reduction. The total amount of concrete placed was just over 12,000 yards or 9,200, you know, cubic meters. So not a humongous job, but a sizable job. Most of it, as I mentioned before, was the post-tension deck. And what we learned from that is, you know, schedule drives everything. You know, the need for it to reduce, to hit that initial strength so we can move our forms is key. That in turn really limits, you know, how aggressive we can get in taking the cement out, because that in turn, you know, retards in many cases getting that initial strength. So we had about a 1,400 metric ton reduction of GHG over business as usual. Again, probably with a different structural system, we could have been a little bit more aggressive with that, but that's the result using the PT decks. I think the bigger story here is that, you know, we started out in the state with 5 EPDs, and after this project, we had 90. And that's because the requirement to produce EPDs was written as one of the contract requirements as we brought on our subcontractor. And they did a great job of, you know, really moving the market forward and giving us great coverage and data on the project. So by volume, 99.7% of the project's concrete had EPD data. So that really gave us good confidence that when we ran the numbers, we had good data behind it. So just, you know, in summary and kind of to a few takeaways, you know, I mentioned this before, but I can't stress it enough. Really be aware of the schedule impacts. And the schedule impacts kind of come in a couple different categories. You know, one is that, you know, R&D and producing the EPDs, that's obviously additional time that you need to accommodate within the schedule and to bring on the partners earlier so that happens. The other schedule impact is that, you know, often when you are taking cement and reducing GHG from a particular mix, it will achieve that initial strength later than maybe a conventional mix would. And so that, you know, that really causes you to think long and hard about what are the best applications and what is not on the schedule critical path that would be a good match for those more aggressive mixes. Mock-ups, big lesson learned there. You know, we hit our strength, you know, on everything, but again, it behaves very differently, you know, if you're testing the strength, initial strength in the lab versus, you know, out on site. Weather and schedule. We had the wettest winter on record when we were building this, and one of the coldest. And that really, you know, just in general, sort of concrete aside, gave us some schedule challenges. And because of that, we had to sub in some conventional mixes to do schedule recovery. So just be aware that, other factors intervene that may limit your ability to use the lower GHG mixes everywhere. And then the next one is the type of structural system is probably the prime determinant on how aggressive you can be. So, when things are not on the critical path or where you need to control, say, the heat of hydration and a mass slab, or, maybe in footings or foundations, that would be a great application. Post-tension deck, you can do something, but maybe not as aggressive as you would want. And then lastly, I just want to close with the point that this is changing very quickly. We're seeing sort of a hockey stick shaped graph of EPDs coming out around concrete. We started with 5. This brought 90 more EPDs online. Shortly after this project, another major manufacturer or producer in this market, invested in EPDs sort of on demand. So another additional 2,000 came on. So this is all great news for all of us on the call that are looking for and wanting the data to proactively plan how we can, take embodied greenhouse gases out of our project and to be smarter about our next projects. So thanks very much, and I look forward to questions from you guys.
Great. Thank you so much, Dave. And thank you, Erin, David, Brad, and Leif for joining us today and sharing your knowledge and insight. This concludes the main presentation part of today's session, and we realize we are going a little bit past time. So if you have to go, thank you so much for joining us today. If you are able to stay on the line, I have a few quick announcements to make, and then we'll turn over to Q&A with our speakers. So if you found today's webinar useful and you'd like to participate in future webinars, our next one is going to be August 17th, and it's going to be led by the Reuse Task Force, chaired by Larry Strain. So I'll make sure to follow up with everyone later today or early next week with how to register for things and any links that were mentioned today. Again, we'd like if you could take some time to learn more about the Embodied Carbon Network and think about getting involved. We are going to have a prospecting and new member introductory call next Friday, June 29th at 9 a.m. So join us if you'd like to learn more. And a reminder too that if you're an AIA member and you'd like to receive a continuing education credit, please send me your full name and AIA member number. We also have some exciting events coming up that the Carbon Leadership Forum is convening and working with a lot of different collaborators to put together. We have one next week in New York City if you happen to be there for the AIA conference. It'll be on June 20th, and it's bringing together a lot of different stakeholders to build a roadmap for a carbon smart building future, especially by 2050 to meet greenhouse gas emission goals. Another really exciting event coming up is going to be in San Francisco on September 11th, and this is called Carbon Smart Building Day, and it's going to be at the, what was it called? The Global Climate Summit. This will be an all-day event followed by a reception, and it's going to bring together thought leaders across architecture, engineering, contracting, real estate development, and urban planning, as well as from the leading green building NGOs. So there'll be presentations and collaborative workshops, and attendees will have a hands-on opportunity to identify steps that we can all take to lead industry transformation. So if you can attend, please register by June 25th, and again, I'll send out links to both of these events. So we'll go over to Q&A now. Let me pull up the questions that we had come through. Okay, so our first question was for Leif. So Leif, someone wanted to know, how do I download and use the specifications?
Well, good question. So if you Google the Carbon Leadership Forum at the University of Washington, there's a tab called Initiatives, and there's Model LCA Specs. and there you can download them. In my presentation, which I believe, I don't know if we're sending out copies of that, I actually included a link in the last slide, a direct link.
Great, thank you, and we'll make sure that everybody gets that. So our next question was for Brad. Brad, someone wanted to know if you looked at the systemic effects, for example, changes to other aspects of the building enclosure and or to operating energy resulting from the different wall systems.
So the short answer is for that study, we did not, and it was sort of intentionally that we made that decision now. And that was just to keep things as simple as possible, and let's really just dive into the materials themselves. If we were to run which we are doing now, a much more intense methodology for a whole building LCA, then absolutely we take into account what is the whole carbon trade-off of adding a triple pane window versus a single or double pane, and how does that affect all the different operational costs and everything else. So it's definitely a much bigger picture when you start to look at the building as a whole and what type of assemblies or decisions affect the project across the board. But with that study in specific, we were really just trying to eliminate things to look at and try to still get some valuable lessons. Part of that study that I didn't mention was also just about learning software, figuring out how much time things take. So it was really a rudimentary way to kind of dive in. And but now, if like I said, we weren't really comparing apples to apples with a lot of those as well, or we weren't even necessarily looking at a whole building's life cycle. Like I said, that would be a much more intense methodology, and I guess one of the best resources to get into that would be to look at the Carbon Leadership's Forum, the Whole Building LCA Practice Guide.
Great, thank you, Brad. So our next question was for David Diaz. Someone wanted to know, don't young plantations grow faster and sequester carbon more quickly than older forests? Why wouldn't that be the best management strategy for getting carbon out of the atmosphere and into wood?
That's a really good question. This is one of the more common ones that comes up. So I actually have a couple slides that I prepared. If you can hand me back control, I can talk through that a little bit.
Yeah, sure, that'd be great. I will go ahead and make you presenter.
But yeah, basically, what this kind of boils down to is a question of, kind of what's in scope when you're trying to quantify the carbon balance of your wood. And so here's a pretty typical kind of explanation that we hear about how the carbon cycle is viewed, the forest carbon cycle is viewed when we talk to folks from the timber industry. And basically what you have here is something where you've got carbon getting sequestered in healthy working forests here on the right. And then over here on the left, you have these old decaying forests that release and store carbon. And in the middle here, what you have is this closed loop where you have wood products going into this vault, right? So there's no carbon emissions that are apparently happening from this kind of sustainable working forestry model over here on the left. And all the emissions are coming from these old decadent forests. And basically leaves out a variety of important things. And a couple of them are that this is kind of showing what's the carbon balance of a forest over time. And so we have this idea, from that previous image that once forests get really old, they're releasing carbon to the atmosphere. And what we find is that that's generally not the case. That younger forests do sequester carbon at a quick rate, but as you get to forests that are 100, 200, 300 years old, they are stockpiling a huge amount of carbon and are holding onto it for a very long time. And so what you want is to try to maximize carbon across the whole forest system. That's products and in the forest. And the other piece of that is, does the carbon in wood products actually get locked up? So this is kind of what happens after a harvest in terms of the carbon proportion and different uses. And so what you can see, for example, is in year one, you've got maybe 74% of any carbon that you harvested in products that actually goes into products, and the rest of it is emitted. And by the time you're at 100 years out, you've only got 13% of the carbon that went into the product that's left. And so accounting for these two things gives you a very different picture of what that looks like. And so here's a different version of the carbon cycle that came up from a peer-reviewed study where the wood product sink looks very different here than it does in that previous story. And then you've got decomposition happening from all forest types. and the fire is not where most of the emissions come from. So I think, you know, dialing those things in makes a very big difference in terms of what type of conclusion you would draw. And in general, most of the recommendation that comes from the scientific community is storing carbon in the forest is the least leaky bucket. You know, trying to store carbon in wood products punches a lot more holes in the leaky bucket, and is harder to kind of accumulate carbon over time.
Great, thank you so much, David. Let's see, I think we have time for one or two more questions. Okay, so this question is for Dave Walsh. Dave, how do you think lower carbon concrete affects costs? Would this negatively impact someone's construction budget?
There's a couple ways to answer that. You know, we were looking very closely, obviously, at cost. And, you know, the cost of cement and the cost of the SCM, like slag or what might be replacing the cement, they're commodities, they go up and down. But, you know, at the point that we were bidding this project, the cost of the SCM was lower than the cement. So, you know, logically, you would think that if you're replacing some of that, that would have a beneficial impact on cost. We found that, you know, of the people that were bidding and the people that are most familiar, we had a very competitive, actually the most competitive bid was the mixes that were most aggressive in terms of reducing the GHG. So from looking just at the material cost side of things, I don't think it needs to be an add. In some ways, it might actually be a cost benefit. But there's a schedule component to cost as well. And so, you know, as I mentioned, if you have some of the more aggressive mixes on your critical construction path schedule, that can stretch out your schedule, and that's big cost implications. So I think the key to making it cost neutral or cost beneficial is to keep those out of the critical path so that you're not negating any kind of lower material costs with extended construction durations. So.
Great, thank you so much, Dave. And our last question is going to be for Erin. So Erin, someone wants to know, as an Embodied Carbon Network chair and someone who is thinking about the larger context of how building materials affect global greenhouse gas emissions, how do you think a group like the Embodied Carbon Network can be leveraged to drive progress and action, to action some of the strategies needed to meet global climate targets?
Wow, that's a really good question. I mean, I think if I thought about that question for a while, I could, you know, come up with a really long answer. But I think what is really clear to me, and I think to most of us working on this and thinking about it at a large and over a long time period scale, is that the only way we're going to achieve our climate targets is by a combination of grassroots, ground up efforts, which have been the efforts primarily driving any progress to date, at least in the US, with really solid and strong top-down or legislative policy efforts. And I think that's, you know, that's where we've been lacking in progress, both in the operations and in the embodied world. And obviously we see some more policy efforts actually legislating embodied carbon coming online here and there, but it's very slow uptake. So I think it's for most of us in the Embodied Carbon Network and for most of us who have been working on this for a while, I think we really have been taking that bottom-up approach, that grassroots approach, and making change at home within our own firms and within our own communities, et cetera. And I think we need to keep doing that, you know, push to do that even harder. But we all really need to learn how to become activists as well, and we need to learn how to you know, both as private citizens and as companies, firms, and a network, figure out how we can really advocate for and push some of these legislative initiatives. Because again, I just without that regulation piece, especially to put in some kind of, you know, some deadlines for when certain targets have to be met, I don't think we're going to meet it at large enough scale to actually achieve our Paris targets.
Great, thank you so much, Erin. That's a great, inspiring note to end on. So thank you again to all of our speakers for taking the time to give great presentations today, and thank you all for joining us. I will send around a link to the recording and all of the slides so that you can look through them later. Again, we hope to see you in the next webinar, and please think about getting involved with the network if that sounds like something interesting to you. Have a great day, everyone, and we'll see you next time. Bye.